Bismillahirrahmanirrahim. Today we will talk about the chapter 8, which is induction. And previously we have talked about the complex numbers in previously we have talked about the complex numbers. So now we will talk about the induction. Let's say, as written here, consider the following three statements, each involving a general positive integer. The statement one is that the sum of the first n odd numbers is equal to n square. Statement 2 is if p is greater than -1, then 1 plus p power n is greater than or equal to 1 plus np. And statement 3 is the sum of the internal angles in an n-sided polygon is n minus 2 into pi. Now, these are three statements. We are talking about the induction. So induction, what is induction? It's a way to prove things. It's a method of proving things, statements, propositions, lemmas, and theorems. We use that kind of thing to prove these statements. If you talk about these three statements, that a polygon is a closed figure with straight edges, such as a triangle has 3 sides, a quadrilateral have 4 sides, a pentagon has 5 sides. Okay, we can check that these statements are true for various specific values of n. For instance, we are checking now. 1 is true for n is equals to 2. So the sum of first two odd numbers is 1 plus 3 is 4, which is 2 square. And for n is 3, which is 1 plus 3 plus 5 is 9, which is 3 square. Okay. The statement 2, which is if p is greater than -1, then 1 plus p power n is greater than or equal to 1 plus np. And this is true when n is 1, is 1 plus p is greater than or equal to 1 plus p. And for n is 2, we have 1 plus p square is actually equals to 1 plus 2p plus p square, which is surely equals to 1 plus 2p. And statement 3 is true for n is 3, is the sum of the angles in a triangle is pi, and for n is 4, the sum of the angles in a quadrilateral is 2 pi. Okay. Now, but how do we go about trying to prove the truth of these statements for all the values of n? That's where we need the induction. The answer is that we use the following basic principles. In it, we denote by P of n. So now we say that P of n is a statement involving a positive integer n positive integer n. For example, we say P of n could be any above 1, 2, or 3. Okay. And by this, we will give the principle of mathematical induction. Principle of now suppose that for each positive integer n, we have a statement P of n. If we prove the following two things, A, the statement is true for 1, n is equals to 1. B, for values of n, if the statement is true, then the statement should be true for n plus 1 values. And this says then the statement is true for all positive integers n. This is the principle of mathematical induction. The logic behind this principle is very clear. By the condition A, the first statement P of 1 is true, And by condition B, when n is 1, we know that P of 1 implies P of 2, and hence P of 2 is true. And by B, when n is 2, P of 2 implies P of 3, and then hence P of 3 is true, and so on. That's how we can prove the things. And then we just need to prove that it is true for P of n plus 1. It may look a little bit strange at the first sight, but a few examples should clarify a lot of matters. So let's give the examples. So let's try to prove the statement 1. Statement 1 was the sum of first n odd numbers is equals to n square. Prove that. So we can write prove that the sum of first and odd numbers is n square. So we have this statement. Okay. Now we need to show, or we can also write this in the numbers way. This is what we need to prove in in these number symbols. So part A is P of 1 is true, which is indeed true, that square 1 square is 1. Part B is, we say P of, assume or suppose P of n is true, which means 1 plus 3 plus 5 plus 2n minus 1 is indeed n square. Then adding 2n plus 1 to both sides gives, adding 2n plus 1 to both sides gives it gives what? It gives 1 plus 3 plus 5, so on, plus 2n minus 1 plus 2n plus 1 is n square plus 2n plus 1, and this gives n plus 1 whole square. If you just keep it same, which is the statement Pn plus 1. Thus, P of n implies P of n plus 1. We have now established part A and B, hence by the principle, by principle of mathematical induction, P of n is true when n is positive integer. Okay. Similarly, we can prove the second statement. Second statement says that we have for n a positive integer, p of n is a statement says that if p of p is greater than -1, then 1 plus p power n is greater than or equal to 1 plus np. Okay, this is the statement we need to prove. And solution for A, observe that P of 1 is going to be what? P of 1 is going to be that 1 is greater than -1. So 1 plus P is greater than or equal to 1 plus P. Okay, this is P of, this is part A. Then for B, we suppose P of n is true. So we are saying that 1 plus P power n is actually greater than or equal to 1 np. This is what we have supposed. And we are assuming that p is greater than -1. We know that then p plus 1 is 0, is greater than 0, not 0, but greater than 0. So we can multiply both sides of the inequality by 1 plus p. So we multiply both sides by 1 plus p to obtain 1 plus p power n plus 1 n plus 1 is greater than or equal to 1 plus np into 1 plus p, and this can be written as 1 plus n plus 1 into p plus np square. Since np square is greater than or equal to 0, then 1 plus p power n plus 1 is greater than or equal to 1 plus n plus 1 into p, which is p of n plus 1. Thus, p of n implies p of n plus 1. Therefore, so we don't write again and again about principle of mathematical induction. We just say by induction. Therefore, by induction, p of n is true for all positive integers. Now, here we will end the part 1 of this lecture series. In the next part, we will talk about the principle of mathematical induction 2.